We want to talk about electric power. We've looked at power already. We defined power both last year and this year, Kenta, as work over time. Power is measured in what? Watts. You've all heard about watts in terms of electricity as well. Light bulbs come in watts. So there must be a way to also get watts from current and voltage and resistance. And there is. Recall, as charges flow through a circuit device like a resistor or a light bulb is a good example of a specific resistor, they lose energy due to collisions with atoms in the wire. So you might be, if the current is going to the right, remember we defined current as the direction the positive protons would move if they could. In real life, it's the electrons moving to the left in this circuit, but current would be moving to the right. It's called conventional current. We just defined it that way because it makes the math much easier. Oh, got a late comer. Have to interrupt my recording. YouTube, a student walked in late, and now I got to remember where I left off, so I'm probably going to repeat myself. This is why I hate it when students come in late. I'm glaring at my student right now, but he's smiling. So in this circuit, for example, if we were at a higher voltage, maybe right here you measured it at 8 volts, and right here you measured it at 6 volts. How many volts did we lose going through that resistor, Eric? Be obvious. And what that really means, because voltage is also joules per coulomb, it means we lost some energy. It was transferred to heat, especially in a light bulb, because you're just heating up the old incandescent bulbs. So since energy lost by the charges is transformed into heat energy, it's related to voltage drop, because voltage is defined as the potential energy per coulomb. So if I just get potential energy by itself, it's QV. Voltage is joules per coulomb. So example 1, let's put that in our back pocket, the idea that potential energy is QV. And let's see if we can use that to come up with an expression for electric power. This is going to be Joule's law. Power is energy loss over time, or it's work over time. Work is measured in joules, so really it's Q. Let's do it this way, Mr. Dueck. It's QV over time. That's still joules per second. And then what does it say in the bracket next, starting with letter G, Eliana? Grouping. What I mean by that, do me a favor, can you circle the Q and the T? And then can you go look on your formula sheet? I think Q over T is something. It's going to be in the electricity section, obviously. Yeah. What's Q over T? Yeah, you saw it. What? What's I and a breathe for? This one you'll have to memorize because it's just doesn't, it's from Latin, current. Okay. So actually it turns out power is I times V, although we usually write it as V times I. Power equals V times I. This is called Joule's law. It's the amount of energy drop per coulomb of charge times the number of coulombs that are coming through per second, in case you're wondering. But that also works out to watts. It works out to joules per second. So the rate at which electrical energy is transformed into heat energy, the rate at which you're using power in a circuit, is power equals V times I. It's also worth memorizing this one. In fact, we have two equations. We have Ohm's law, which I gave you on your formula sheet, V equals I times R, and we have Joule's law, power equals I times R. How many variables, how many different variables grand total are there in those two equations, Ashley? 5. What you're going to hear me say for the rest of this unit is anywhere in a circuit, if I know two things, I know, sorry, is there 5? There's 4. I said 5. There's 4 variables. Geez, Dueck. If I know two things, I know 4 things. Okay? If I know two things, I can find all four. And we're going to start to use that to solve circuit. In fact, we're going to do one little trick right now. Example 2 says use Ohm's law, V equals I times R, to find two more relationships for power dissipation. Well, the first one would be replacing the V with I times R times I. But Jay, what's a better way to write I times I? One version is I squared R. This is the one that I end up using the most just because more often than not when I'm solving a circuit, I know the current and I know the resistance. It's not like it's more useful. It just happens to be the case. Or I could have got the I by itself. I is V over R, and so I could write this as V times V over R. Although, Dean, what's a better way to write V times V? In fact, power equals V squared over R. There's three versions of Joule's law. It starts out as power equals P equals V times I, and it's also I squared R or V squared over R, which is why I said if you know two things, you know four things. I'm trying to remember, did I give you all three versions on your sheet? I used to not, so I guess I'm mellowing as I get old. Okay. Where do we use this? Oh, technical comment here. Again, because I'm nitpicky. Uh, in finding the energy lost by charges, I should really use the work energy theorem. Work equals the change in potential plus the change in kinetic. This is a different way to write that my friend who typed this up uses, but that's still the work energy theorem. You may have noticed right when you flick on a big appliance, the lights briefly dim for a split second and then go back to normal. That's because the charges went from being at rest to in motion, and there was a tiny bit of kinetic energy required as well. But once they hit steady speed, there's no change in kinetic energy. And so technically, we're ignoring the change in kinetic energy, even though right at that split second, you may have seen there's that little dimming. We're just going to pretend that doesn't happen. So we can write the voltage drop. We write voltage in place of the more correct delta V because we're lazy. And so this is why we can say work energy loss is QV. This is why we're able to say power equals V times I. All right, let's use this. Example 3. I'd kind of like to say I like example 3, but too easy. But this gives you an idea of how we're going to start to solve circuits. Kyle, what does example 3 want me to find? Okay. What's our symbol for current? I equals? All right. What's that 1400? What is that 1400? I know it's watts units. What is watts a measure of? Starts with letter P. Okay. Power is 1400. And what else did they give me? Look at the circuit diagram. Voltage. Now this is AC. A symbol vanished. If you look in that circle, the symbol for AC is a circle and the little sine wave. For some reason, over the years, that sine wave has vanished. Can you draw it in there for me, please? Symbol for DC source, right? The left side is negative, the right side is positive. The symbol for an AC source is not negative or positive because the current is going back and forth. Everything that I teach you, though, is applicable to AC circuits, even though we'll be looking mostly at DC. So I have this. Kyle, I would say I'm looking for an equation that has a current, power, and voltage in it. There is one. Joule's law. Power equals V times I. I'm trying to remember if I go back to the previous page. You know what? In the previous page in the box, you can, if you want to, in quotation marks, put Joule's law. I don't think I referred to it in the notes that way, but it's what it's called: Ohm's law and Joule's law. Kyle, how would I get the I by itself? Yep. It's going to be 1400 over 120, which is what? What do you get? Units, current. I guess 11.6 repeating, probably, right? Yeah. Units, current. We had our grad prom and dance, Mr. Yeah, I know. What's current in? Amps. Okay. You want to have your units by the end of this week for sure. Really, you want them by Wednesday for sure. But again, don't make flashcards. I think I'll do enough of them that you'll just figure it out. A standard household plug, a standard household circuit can handle 15 amps safely. If you put in more than 15 amps in older houses from the 50s and 60s, you'll blow a fuse. In modern houses, you'll trip a breaker. Could we plug two blow dryers into this circuit? The obvious. Ruby. No, you'd be 22 point or 23 point whatever amp. Yeah, you'd blow breaks. Okay. So blow dryers take a lot of amperage. Why? Well, the more heat you're moving around, the higher your wattage. I'm not going to ask you this on a test. This is just to give you an idea of really high and really low. I've randomly scrambled a bunch of appliances in the left column, and in the right hand column, I've got the approximate wattage. Look at the appliances. Which one of those do you think is moving the most amount of heat around? That's going to be the one with the highest wattage. And your hint is if you pull it off of the wall, it actually has a special 220 volt outlet, has a massively thick cord. There is one of these devices that has the highest wattage. Arian, which one do you think it is? Yep. Clothes dryer is usually just under 5,000 watts. That's the highest number over on the right. Which one moves the next largest amount of heat around? Ella, what do you think? And I'll give you, it'll be the 3,200 watt one, but which, it's not the kitchen fan straight across from it, I assure you. Which one do you think moves the next largest amount of heat around? Take a guess. Not quite. That's going to be the third one coming up. There's one that moves more heat around than that. Your hint is the word heat is in the name of the device. Hot water heaters, you're probably your next biggest drainer. Those are usually around 3,000 watts. Now that's if you're using an electric hot water heater. Some of your houses might be natural gas hot water heaters. Ooh, here's one I think that's probably pretty easy. Even Fahim can get it. Average light bulb wattage, Fahim. I'm going to make the assumption that you've replaced a light bulb. Look at the remaining wattages. Which of those is your standard incandescent, not LED bulb? Now we're finding out if he's ever had to. Yeah, I know you're all wondering how many Fahims does it take to change a light bulb, right? Yeah. Yeah. Wow. Wow. Who's replaced a light bulb? What are standard light bulbs in a room? 60. Fahim, I'm going to email your parents and ask them to make you replace light bulbs from now on. 800. A 120 watt bulb would throw enough heat on you that you'd start to sweat. An 800 watt bulb would probably be uncomfortable to even be in the same room with. Um, really, really bright stage lights that the actors sweat under, those are probably about 300 or 400 watts. Let's go the other direction. Which of these do you think uses the least wattage? And your hint is it runs off a tiny battery that I only need to change every year or two. Ruby. Yeah, wall clock, that runs off a single AA battery and it lasts about a year. So it uses very little wattage. It uses very little joules per second. Uh, what's the next smallest? And it's the next one that's left here. Your hint is because you're using it to cool things down, you don't want it to throw off a bunch of heat. Okay, yeah. Those are usually about a 150 watt motor. If you're running your kitchen fan, put your hand on the motor. It's warm-ish, barely, but it's not throwing off a lot of heat. Okay. Large microwave. Large microwave is usually around 1200 watts or 1.2 kilowatts, and a computer usually uses around 800 watts, 800 joules per second. Basically, the more heat an appliance moves around, the higher its wattage. So a kettle, probably around 1500 watts, hair dryer, 1400 watts. Both your hot water heater, certainly the other one is your stove. Your stove, if you have an electric stove, electric oven, and your dryer, if you pull both of those off the wall, you'll see those have 220-volt outlets. They're specially wired in, and those, I think, handle 30 amps. Almost all of your other circuits are 15 amps, unless you also have a fast charging electric car power station in your garage. Electrical energy, since power is energy over time, you can also solve for energy. Energy is going to be power times time. We have a bit of a problem. Look up for a second. Energy, electric field. Energy, electric field. Energy. Have I mentioned we don't have enough letters in we just don't have enough letters in the English alphabet, so don't get them confused. Since a joule is a very, very small unit of electric energy, it's common to, sorry, I should have showed you where this came from. Remember, power is work or joules over time. I got the work or the joules by itself, but now instead of calling it work, I'm going to call it electrical energy. A joule is a very, very small unit of electrical energy. If your parents got their electric bills in joules, they would be in the billions of joules and they would freak out. And so we have another unit that we use. It's called the kilowatt hour. Now, kilowatt, that's watts, that's power. Hour, that's time. That is energy. It is power times time. But if you get your electric bills, BC Hydro will charge you in kilowatt hours. 1 kilowatt hour is 3.6 times 10 to the 6 joules. A typical house uses about 1,000 to 3,000 kilowatt hours of energy per month. So how do you figure out your electric bill? If a 60-watt bulb is left on all month, 30 days, 24 hours per day, find the amount of energy it will use in joules. Victor, what does part A want me to find? I think I heard a phone. Someone wants to make sure that's on vibrate. Energy is power times time. Power is easy. How many watts is this bulb? Yeah. Fahim, how many watts is this light bulb? Not 800. Time, well, it's going to be 30 days times 24 hours times 3,600 seconds per hour. How many joules of energy will one light bulb use if you left it on for a month? And you're going to get a big number. I get a 1, a 3 fives, a 2, and 4 zeros. You know what? I was going to write this in scientific notation, but I'm going to write the 1, the 3 fives, and the 2. It's less work just to write the 4 zeros. I'm going to do it that way. 1, 3 fives, a 2, 1, 2, 3, 4 zeros. Victor, you got that same number? 155 million joules of energy. One bulb. This is why your parents, and this is why when you start paying your own utilities, you won't get a bill in joules. You can imagine people would freak because they don't grasp numbers that large. They don't have a good number sense. So what BC Hydro does is it gives you that in kilowatt hours. We're going to do a conversion. So I have 1, 3 fives, a 2, and 4 zeros joules. I want joules to cancel. Where am I going to put joules, Eric, in my conversion factor? On the top or on the bottom? Remember good old physics 11? On the top, it's going to be kilowatt hours, and the conversion factor, 1 kilowatt hour is 3.6 times 10 to the 6th joules. Again, you don't need to memorize the conversion factor. If I give you this on a quiz or a test, I will give you the conversion factor. It was times 10 to the 6th. Yeah, okay. So I'm just going to go answer button divided by 3.6 scientific notation 6, and you get a much nicer number for adults to wrap their brain around. You get 43.2 kilowatt hours. That they can grasp. I actually changed the numbers this year. BC Hydro, I looked up the rates 1 month ago. They charge 9.6 cents per kilowatt hour. So how much money will this cost you? You'll go 43.2 times 9.6. And then if you worked for Verizon, you would say that's $414.72. It's not. That's 414 pennies. So $4.15. Yes? Divide by 100 if you want to convert it into dollars and cents. That's a problem. That's leaving a bulb on for an entire month. It's not that expensive. I mean, it adds up, but part of the problem we have is we're good at making electricity for cheap. So why do we ask you to conserve energy? It's not just for the money. I mean, it does add up. It's for the environment. In the 30s, 40s, and 50s and 60s, we built a bunch of hydroelectric dams. BC has fairly clean power after the fact. But those hydroelectric dams really ruined our fishing industry. We didn't know at the time. When I was a kid in grade 3, I had to do a report on the fishing industry in BC. At that time, it was the third biggest industry in British Columbia. I'd be stunned if it's even top 10 anymore. And also, we created a bunch of lakes. We flooded a bunch of areas. All the trees that we flooded, they're now releasing their carbon into the atmosphere. That's also not that good. Again, we didn't know any better at that time. Now, what we're saying is, hey, let's see if we can use what we got and not have to make more. What's your homework? Shorter lesson today. We're also going to go through the gravitation test today, by the way. You can try number 1. 2 is good. 7 is good. We're just going to pause there because I think a lot of you owe me homework from the previous lessons too. So let's go like this, Mr. Dueck.